This talk is kind of continuation after 3 years talk which I gave. It was 23 about non-holomorphic Landau-Ginzburg model. At that time it arose from some discussion with Ludmil and Denis. But there are actually some open questions in the talk, and I hope to give some answers to these questions. Yeah, so let's recall what is this B-model dual to Fano variety. What is the best case of such Landau-Ginzburg model? When you get a smooth quasi-projective variety Y or complex numbers with algebraic volume form and a map to a affine line or function, which is a proper map. So generic fiber is a smooth Calabi-Yau of dimension n-1, and then some fibers degenerates. And this choice of volume element is typically unique. If generic fiber is connected, then the isomorphism is unique up to a constant between canonical bundle and shift O. Yeah, I remember only Landau-Ginzburg model for Pn, like for P2. Okay, what is it? Variety is what is variety? I will tell you in a minute. It's the risky open part. It's a torus, C star square, and the restriction of potential to the torus is the usual Laurent polynomial, z1 plus z2 plus 1 over z1 z2, or sum of 3 coordinates when the product of coordinates is equal to 1. And if you look on this map, which is not proper, the fibers are elliptic curves, minus 3 points, and in symmetric form it's obvious what are points, which you remove from elliptic curve, namely assume that 2 coordinates are very big complex numbers, z1, z2 say. Z3 then it will be close to 0 because the product is 1. But z1 and z2 should be almost opposite to each other, so the sum has some finite limit. And then you add permutation of indices 1, 2, 3, so you get 3 missing points at infinity for any fiber. And how to describe this variety geometrically? At 3 copies of a affine line to C star square. And what is it? You consider a Poisson toric surface corresponding to this fan, which consists of just vertex and 3 rays, nothing in between. So it's C star square and union of 3 C star. You have this a bit non-compact toric surface. It's Poisson surface. You just extend obvious holomorphic symplectic form to the boundary. It vanishes in the boundary. And then on each boundary divisor, you take point with coordinate -1, like sum of 2 numbers is equal to 0. It means that their ratio goes to -1. You make blow up at this point. When you make blow up, the symplectic leaf became larger until you get 3 affine lines, and this will be your variety. It's and this non-compact variety is mirror to CP2 minus smooth cubic curve. And the same thing works for mirror CPN. Again, you get open part, which is n-dimensional torus, and the potential is the usual one. Okay, and in this, the best case of mirror symmetry, you have DG or Lie infinity algebra, depends on how you calculate direct image. Namely, consider variety Y within the risky topology. As algebraic variety, you get sheaf of polyvector fields, and consider differential commutator with function, it's Houghton bracket. So you get a sheaf of DG Lie algebras, and take R gamma in whatever model you get some Lie infinity algebra. And they claim this is homotopy abelian. So this, if you try to solve Maurer-Cartan equation, you get a formal germ of supermanifold. And this supermanifold will natural base of formal F bundle. Why is this smooth? It's come from two facts. First of all, remember we have algebraic volume element, which identify just as a complex. This R gamma identified with, instead of polyvector fields, you get forms, and differential became multiplication by df. Okay, so and this things looks like Hochschild homology when perturbed by function f, which element in HH0, so you break the grading, keep only the two grading. And then in such situations, there is a generation of Hodge-to-Durham spectral sequence, which we proved a long time ago with Baranikov, and then it was periodic proved by Volgodsky and August. Namely, what is going on? You add some formal parameter u, and deform differential, add to df Durham differential with small parameter u, and they claim that this guy will be free module over form power series. Actually, it's formal version of this degeneration, which is a bit easier. Yeah, and just for these two facts that you get this Bartalin-Minkowski algebra in subdegeneration, you can deduce that the formal modular space is abelian, is smooth, or algebra is Lie infinity equivalent to something with zero bracket. Yeah, and the question is, does this formal germ naturally extends to analytic germ? As this question, and what I want to say, the answer is yes. And but before explaining the answer, let me tell you that that's really complex analytic question, not a question of algebraic geometry, because it will be the germ will have non-natural algebraic structure. When the function has isolated Morse singularity, like for mirror CPN, and the analytic structure is obvious. All deformations just move critical values in completely freely. They move as they want, and you get locally just domain and configuration space of C, space of critical values. Globally, the thing is kind of complicated. It's not algebraic variety, and you get something like Penn-Levé equations, isomondrome equations, and when you move the things, you also get isomondrome deformation of some bundle with regular singularity connections, regular singularities outside of critical values, and these connections will be in general not algebra geometric. You cannot really write formulas for them already for CP2. And on this huge analytic Frobenius manifold, you have only tiny part when you get things which belongs to big algebraic geometry, Picard-Fuchs equation. For example, for this CPN, you get n+1 dimensional parameter space, but only two-dimensional part. When you just rescale and shift your potential, or in terms of critical values, you get vertices of a regular n+1 gone. Then you get algebra geometric situation. Otherwise, it's some strange connection from which you can expand to some parameters, but cannot really write. Okay, so now I want to explain why things analytic, and I just want to strip all unnecessary assumptions. And what I'll consider, it's question not on algebraic geometry and analytic geometry. Now consider holomorphic map, draw some smooth complex analytic manifold. Map is no longer proper. And the only assumption which I want to keep is that the critical locus, the set of points when derivative is 0, is compact. That's it. And in fact, my manifold I can replace by arbitrary small neighborhood of this critical locus. And what I'll tell you, it will not change under this shrinking. Yeah, so we have DG, in this case we have DG algebra, not the infinity algebra. You consider Dalbo resolution. Namely, what you do, you consider polyvector fields in holomorphic direction multiplied by forms in d-bar direction, and differential with now sum of two guys commutative with function and d-bar differential. Yeah, now there is some kind of like rules of good behavior in analysis. Yeah, traditionally people consider C infinity stuff, yeah, like C infinity resolution. It's good for some things have partition of unity, but really good for very few things. It's much better to consider real analytic sections instead of C infinity sections. And why it's better? Yeah, if you have complex manifold and consider real complex valued real analytic functions, complex manifold. What is it? It's actually functions. We can describe these things holomorphically. Your manifold you embed as a closed subset in the product of itself with a complex conjugate. It's kind of like diagonal. So you have y cross y bar. Now you get totally real analytic subset y diagonal. And now consider functions, holomorphic functions on the product guy in the neighborhood of the diagonal. And that will be real analytic functions on a manifold. And you see, so you get kind of like product structure, and then these things will be really completed as a product. You get separately z and z bar coordinates in this way. Yeah, okay, it's just make things kind of easy to visualize. And another kind of good advice to do analysis, we have non-compact manifold Y. And we have this non-compact Y diagonal sitting in Y cross Y bar. It's better to replace Y, or kind of Y diagonal, by any compact subset. And without any conditions, any regularity conditions, any compact subset will work. And in order to keep track of my critical loci, I want this compact subset, besides that its interior contains critical locus. So on the boundary there's no critical points, but it will be an interior. Why it's a good situation? So instead of Y diagonal, we'll have this compact subset K, and it's totally real. And this is some kind of like Stein compact. So Stein, it means that there are plenty of functions. There's no hypercohomology of functions. So it's a Stein compact. And now consider functions holomorphic in the neighborhood of Stein compact. It's a very good algebra. It's Noetherian algebra. It behaves like algebraic geometry, like chains of ideals are finite. You always get, yeah, that's the best algebras which you can have. It's absolutely parallel to algebraic geometry. Yeah, so that's, one can have intuition from algebraic geometry of possible finiteness in this case. Yeah, so get much nicer functional analysis. Yeah, maybe you heard there was what was called can you remember those Clausen and Scholz developed some condensed mathematics, yeah, using some horrible set theory, some whatever things, and then a couple of years ago, Yefimov and Clausen simplified things enormously. Yeah, so they discovered right class of nuclear Fréchet spaces, which really related to this complex analytic picture you exhaust like Stein domain by Stein compacts from inside, something like this, and then this you get perfect some category, tensor category with colimits, it's all nice property, and that's a way to algebraize analysis here. Okay, yeah, so it's that's right things to do, this over-convergent series, or whatever. Okay, yeah, so get this a little bit analytically better algebra with the same cohomology. You just change some functionalized decoration, but you get this algebra GK analytic. And yeah, so get DG Lie algebra and cohomology of the complex. It's easy to prove from compactness of critical locus. In certain filtration, it will be the leading term of differential, this commutator SDF. You can conclude that the cohomology is spaces finite dimensional. Yeah, finite dimensional is actually very nice because it's finite dimensional space. It could be tangent space to complex variety, or maybe it's DG manifold if it's abstracted, not homotopy abelian. And complex varieties are, nobody has doubts what is it. Infinite dimension will be much worse because people have some series of Banach manifolds, but it's ugly. And here it's kind of right thing. That's a really canonical thing. Yeah, so I claim this canonical germ, analytic germ of DG manifold, holomorphic DG manifold in such situation. Maybe it can follow from abstract story about DG Lie algebras with right functional analysis. It's not clear for me. But the germ one can describe, I'll just sketch, gives the idea in pretty straightforward way. So if you have want to have this Maurer-Cartan space as analytic germ, not a formal germ, it should give you a functor from germs of DG manifolds with some base point to some simplicial sets, something like this, because you should have like maps and homotopy between maps and so on. And this functor should be representable. Now, so we want to describe some kind of functor from analytic germs of DG, maybe analytic spaces, not necessarily manifolds, to my target. Oh, suppose I have super germ of superanalytic space with odd homological vector field, Venchika's base point. What should be a family of solution of Maurer-Cartan equation of this guy? It's very easy to formulate it. You forget about odd homological vector field. So we want to have a map from this germ to the space of shifted by parity my Lie algebra, which is some infinite dimensional guy. But Lie algebra has some meaning. It's some functions of polyvector fields somewhere. And the maps to the functional space, it's like adjoint functors. You can say literally what is it? You consider product of your variety y times y bar times this base, because here in y bar you get this compact where we have to solve things, and consider this polyvector field holomorphically depending on parameter. Everything now became holomorphic, and Stein, it's a lot of functions, no things about cohomology. And now you say that it things kind of is invariant under vector odd homological vector field. It will be some equations. Yeah, so say what are points of the simplicial sets, and similarly say what are one simplices and so on. Yeah, so the questions contains the answer. You have immediately know what functor you represent, and that's actually how people in traditional deformation theory and algebraic geometry prove existence of modular spaces of something. They really say what is a family of, I don't know, varieties, vector bundles, and so on. And then the proof that the guy is representable, there is something called Artin representability criterion. And my guess is here there will be some analytic version of it. You just already know the answer. And to see that the function is representable, you can see it kind of pretty directly using some coverings and so on. Okay, yeah. So it's, so this analytic germ should exist for free. Yeah, but now I didn't put any assumptions except critical locus is compact. And now we want to add these things. First of all, for this analytic germ, you get like factorization property over connected components of critical locus. So 28 will be one of result according to abstract and 20U talk. And is this F manifold business, F bundle business? It was exactly decomposition theory that if you have different critical values, then decompose the product. Here it's a bit more fine because not different critical values of function, but different connected components. You're going to have several connected components with the same critical value. And the reason is kind of clear because you can, this DGL algebra will be replaced by quasi-isomorphic, and functor will be also this analytic germ will be quasi-isomorphic in analytic sense. If you restrict to arbitrary relatively compact neighborhood of your critical locus, and then you surround each component by its own critical epsilon neighborhood, then you get product structure, and then automatically you get product structure there. So first thing it's kind of like product. Then our connected components. And now for each connected components of the critical locus, one can make its boundary more convenient, not just arbitrary compact subset whose interior contains this connected locus, but actually a real analytic submanifold with corners, and whose interior is a full dimension. The corners will be up to codimension 2. So the guy will map to a disk in C, with real analytic boundary, and this guy will have two parts of the boundary, horizontal and vertical, and kind of horizontal part of the boundary will map as a fibration on the disk, and the vertical part of the boundary will map as a fibration to the boundary of the disk, and some components of critical loci. You can make maybe several components you can put in this situation. Components of the critical loci map to finitely many points on the disk. If you get such picture, it's analog of this global vanilla situation when we get global map and we get kind of like Stokes data, not only the product structure on the base of F bundle, but some Stokes data. So what you get in these things? You get map from something to the disk, which is fibration outside of finitely many points, and then automatically you get topological version of perf 0, kind of constructible sheaf with finitely many points with R-gam equal to 0. Namely, you get constructible sheaf on this disk, taking the stock will be the following. Consider cohomology of pair. Totals this domain, which K, which relative to the fiber, and it's local system with fiber smooth, and it gets something else, and fiber singular, and it will be perf 0 sheaf. Now, so it's exactly this gluing data in our old paper with Ludmila Tony. And if you go to union of neighborhoods of connected components, you lose this data. this additional small data, but modular space will be the same. It will be the same product. Yeah, okay. It's just how to recover, if you want, the Stokes data. And now, if you want smooth modular space and so holomorphic volume element and the generation of Hodge-Rams spectral sequence, you just assume that there is a holomorphic volume element and the spectral sequence degenerates. That's it, yeah, and that's it automatically in place. You get a maximal F bundle. If you don't assume, you get kind of derived and non-maximal F bundle, because if you don't have volume element, morally the tangent space to the will be Hochschild cohomology, fiber with Hochschild homology. They have no reasons to be related, and there's no reasons to modular space to be smooth. Okay, yeah. So I got this story, but now again I don't assume anything. Just accept the critical locus is compact, and consider points on this germ of Maurer-Cartan space, which is kind of exotic. It's not holomorphic manifold with a function, but something more tricky. Yeah, why one should consider it? Yeah, again, this like theory of atoms, we should move on some in many parameters in Frobenius manifolds, not only along second homology, and definitely we lose. We solve Maurer-Cartan equation some larger locus when we lose algebraicity or analyticity. Yeah. So what is solution of Maurer-Cartan equation? Just let's follow the definition. It's an element of my odd element of my de Gilles algebra. So it's a finite sum. It will be I vector fields and J d bar forms, and I plus J should be even. So these numbers I and J should have the same parity. So you can decompose this big finite sum. The first term will, by total kind of I plus J weight, will be gamma 0, 0. Then get gamma 2, 0, gamma 1, gamma 0, 2. Then get 5 terms. Gamma 4, 0, gamma 3, 1, gamma 2, 2, gamma 1, 3, gamma 0, 4, and so on. And then at the end of the day, get gamma n, n. Again, one term. Okay. So you get finitely many tensors. And they satisfy some Maurer-Cartan equation. It means that for each total odd degree, you calculate what you see in the corresponding components of Maurer-Cartan equation, you get something like d bar of one component plus commutator with another component plus sum of commutants is equal to 0. Yeah, so you get kind of clean equation in differential geometry. These guys will be real analytic mixture of polyvector fields and forms. And if you look on this equation, you can see just the very corner of this equation, and then you see the following. This component gamma 0, 0 is just complex valued function. It's a non-holomorphic retribution of our original function. You add to function gamma 0, 0, and then components gamma 1, 1 is a Beltrami differential. It's d bar 1 d bar form with values in the holomorphic tangent vector fields. Yeah, this Beltrami differential, if it's sufficiently close to 0, defines an almost complex structure. Namely, when you have Beltrami differential, consider the pointwise as a map from 0, 1 component of the tangent bundle to 1, 0 component of the tangent bundle, complexified tangent bundle. And you can see the graph of this map. So it will be close to T01. The graph T01 is opposite to its complex conjugate. And if you consider little perturbation of consider solution Mark-Cartan equation sufficiently close to 0, then on compact it will be uniformly close to 0. So you get this oppositeness everywhere around this compact, and you get almost complex structure. Yeah, so, yeah, like for a curve, if Beltrami differential has like norm less than 1, then it gives an almost complex structure, and then it kind of breaks to give almost close structure. So it's sufficiently close to 0, get almost complex structure. And kind of the simplest component of Mark-Cartan equation says that near this compact, this here perturbed function, which is close to f, is pseudo-holomorphic with respect to almost complex structure. And then you get some other fields, but let's just concentrate on this property. So you get a non-holomorphic map. You get some map to C of some domain, which is pseudo-holomorphic with respect to some almost complex structure. I claim that it automatically have only finitely many critical values. Why so? Let's try to think it, because map no longer honestly holomorphic with respect to original structure. It's kind of real analytic map from neighborhood of a compact to plane R2, which is C. And in general, if you get real analytic map from real analytic manifold to R2, what typically what happens is that critical values are either isolated points or you get curves, or get real curves. And along the curve, generic point of the curve, get a fold. So in some local coordinates, like for real analytic manifolds, you get map depends only on two coordinates, and x goes to x squared and y goes to y. So you have a fold, and the image will be locally half plane. Yeah, it's elementary kind of singularity theory of maps. But if you have a fold, then the generic point of the fold, the rank of the tangent map, real rank, will be 1. And it's impossible if map is J holomorphic. The rank will be 0 or 2. Yeah. So it shows that folds do not exist, and this automatically has singularities only at isolated points. And then when you have singularities only at isolated points, it's not this complicated cusp curves, then you get perp zero Schiff. Okay, yeah, so it's the object is something very nice. It's a so we get some non-holomorphic gadget which maps to C, and to get only finitely many critical values. For the description I use some kind of like reference integrable complex structure and holomorphic map. I perform this whole things, but in the argument I use kind of only perturbed almost complex structure and perturbed map. Let's call G tilde and F tilde. And one can formulate this notion without using this reference point which we deform, and say, I think the nose, we get almost complex structure, we get non-holomorphic map to C, it's just kind of like two fields, like 0, 0 and 1, 1 component, and then collection of some other tensors which I missed. So we think this is 2, 0, 0, 2, 4, 0, 3, 1, 2, 2, and so on. All except 0, 0 and 1, 1. So you get this collection of plenty of tensors and satisfying some equations. It will be an analog of Mark-Cartan equations, and it's generalized something which was already generalized complex structure by Marco Galtieri after suggestion of Hitchin. It has many more components, like 2 to the power of 2n components, something like this. It's huge amount of tensors. And generalized complex structure by Galtieri, it's a specific case of this very general gadgets when function is 0 and you solve Markov-Artin equations in kind of total degree 2, 2, 0, 1, 1, and 0, 2, which actually coincide with the equation for kind of quantization as the graded category. So it's, the suggestion there is this kind of nice notion of some supermanifold with certain structure, with generalized almost complex structure, and instead of compactness, you consider compactness of the critical locus. Only compactness of the critical locus. If the function is 0, it means that the manifold is compact. But it's some big generalization of generalized complex geometry. Actually, there's something I want to say that these guys solve equations for polyvector fields, which by formality theorem is equivalent to deformations of categories in certain sense. So one can hope that these things will, at least in certain domain, in maybe certain open constraints, correspond to something which you can call like Z2 graded analytic non-commutative spaces. Because you, by this deformation, you lose commutativity, you get like Poisson structures and so on. So what one can do with these generalized objects? Again, if you imagine we start with some reference point, some good holomorphic map, and we get some Keller metric, and suppose we take this compact surrounding singularity such function that its Keller form is kind of like convex on fibers of this map near the boundary. So one can speak about compactness of pseudo-holomorphic disks. Then the same will be true under little perturbations. This kind of the same form omega 1, 1 will be compatible with new almost complex structure. And then you get a map. And the map will have symplectic fibers outside of these critical values. So it means that you can speak about Foucault's ideal category for those guys. Although nothing is holomorphic, you get Foucault's ideal category and get semi-orthogonal decomposition of this category, and corresponding to components will be connected, pieces will correspond to critical connected points of critical locus, and each should choose this Gabrielov path, which I explained in the previous lecture, to get actual semi-orthogonal information. And if you start with a story when you have holomorphic volume element in the neighborhood of critical locus, and the generation Hodge drums, they get deformed things, you get deformed exponential integrals and hypothetically a family of Brigian stability structures. So it's kind of sign why you should get stability structures in semi-orthogonal decomposition in a model description. That's I already mentioned phantoms in my first lecture, that one can potentially get phantoms through some tricky tools. But here again, let's return to situation totally general without volume element, just compact critical locus. Here can have kind of phantoms because for each component of critical locus, you associate analog of this Hochschild periodic cyclic homology with homology with coefficients is vanishing cycles. Or you take a nice little neighborhood, you consider homology of pair, this little neighborhood, and preimage of a smooth point. This will be homology of vanishing cycles. And this guy vanish. Yeah, I can imagine, for example, the following scenario. Imagine that you do complex dimension 3, and your critical locus is elliptic curve, and it's Morse-Bot singularity. So transversally you get quadratic form, sum of two squares. But now I can imagine that you twist the things, so the homology of the sphere, if you go around one of loops and a torus, will have monodromy -1. Then you get homology of elliptic curve with coefficients non-trivial local system, you get 0. Yeah, so it's very easy to cook, like Morse-Bot singularity even, which kills this Hochschild homology, a periodic cyclic homology. And there is an analog of Hochschild homology, or literal Hochschild homology in deformation quantization. You consider now instead of polyvector fields forms with differential df. And again, one can easily construct situation then for some critical locus, this homology is 0. So it means that Hochschild homology is 0, negative cyclic homology is 0, periodic cyclic homology is 0. So you get kind of phantom, not visible through anything. And yeah, I mentioned that by deformation quantization we accept analytic space. How to deal with phantoms? Yeah, usually homology it's some kind of like signature of your category or variety. It's something you kind of try to distinguish one thing from another, so hot theory. And if things vanish, what goes on? How you specify your category? I claim that you always get non-vanishing Hochschild cohomology. Yeah, in kind of like abstract category theory, it's kind of clear. If you get category which is not 0, then the identity functor is not 0. Then the identity map from identity functor itself is not 0, and you get non-zero class in Hochschild homology, home from identity functor to itself. Yeah, so Hochschild homology for non-zero something is non-zero. That's the principle. And here, in kind of like if you don't really do deformation quantization, it's also true. If you get non-empty connected critical locus, or just connected components, non-empty, yeah, that's the main thing. Then in analog of Hochschild cohomology, which is what you consider sections of around this critical locus of my polyvector fields d bar form with this differential perturbed differentiation by some solution. The element 1, which will always element of this guy, because commutator of 1 with everything is 0, and d bar of 1 is 0. I claim it's not 0 in cohomology. How to prove it? And again, it's a very elementary geometric argument. Suppose you want to represent 1 as a coboundary of some odd element of the complex against some j, and you calculate this boundary and calculate what is what will be 0,0 component of this guy. In 0,0 components, it's d bar will not give 0,0 components. It gives only positive green d bar direction. So only it's things which come on from commutant. So it's commutant of mu10, which you take coboundary with perturbed function. And these things, so get kind of like a vector field in holomorphic whatever direction, and some perturbed function, and to take derivative of this guy. And of course, it vanishes at critical points of the function, this guy. So it couldn't be equal to 1, because the critical locus is not compact, and you see that this function should be under 0. Yeah, so it proves that this Hochschild cohomology is kind of right signature, and I suggest to think about categories. The main thing is they're modular spaces, or it will, and if it's not 0, it will have at least function 1. How you shift this critical value. Yeah, and now what I just want to say is that it's when you put additional constraints to be homotopy abelian and get maximal F bundle, then for such gadgets, one can define atoms in the same way as we do in kind of algebraic situation. Again, considering deformations all directions, it will be similar to the question which I asked in symplectic topology, deform along all even cohomology. Yeah, so there is some kind of like atomic objects which you deform, they never split to several of them. And in principle, one can define atomic object even without this assumption of homotopy abelian and maximal F bundle, because we really don't care about fibers of F bundle anymore, looking just on orderless space. What will happen when you consider solution of Mark-Cartan equation? Because locally it will be zeros of odd germ of analytic vector fields on some supermanifold. It will be some analytic germ of some singular gadget, finite dimensional gadget. It has several branches, several irreducible components, and then for each irreducible component, one can try to see again, is it split or not for generic point? Yeah, so one can repeat notion of atoms in this situation, and maybe I just finish this. Is, one can show some very simple result, not so simple result. If you start with compact variety, you start with compact complex manifold with 0 function. Of course, you can deform function by adding constant, but it will be still one critical value. And the claim, if you try to solve these things in this DGL algebra, you never get multiple critical zeros, and the reason because you get almost complex manifold, you get holomorphic functions almost complex manifold, compact complex manifold, and there is some kind of like maximum principle one can prove. So this function should be constant. Yeah. So that's this guy's like compact complex manifold, and there's this very, very generalized deformations are examples of atomic objects in this situation. Okay, so I finished a bit earlier than I should. Okay, thank you.
Questions?